Let's see how we can run the GROMACS now. In the last video, we have installed it, and let me clear it, and we will check that either GROMACS is installed or not. How we check? We check it GMX, and then we ask it version. So it says me it is installed. GROMACS is present at this particular position. So which tutorial actually we are gonna use? We are gonna use a very simple tutorial of the lysozyme simulation actually here for our test purpose, and then we will go to the real-time example. So first of all, we will just use this command wget, and then we use this file to download, which is from 1AKI I will press enter, and here you can see that it has downloaded this particular thing. Okay, but first I will prefer, why not we make a directory which is called test. This directory is empty, so we will go to cd test. There is nothing inside, and actually we try to download this particular file in this thing, and here you can see that we got here 1AKI. So now we have downloaded our protein here. So let me copy and paste this command actually for you people. So I will send you the file for the next time, so it will become very easy for you to do the practice. So this is how we download the file, and next is to extract the waters from that particular file. That we can do by using the pymol, but there is also a command, grep command, which we can use here. Let me use the grep command for it. So this is lysozyme tutorial actually, which we are gonna follow for our thing. So we will download file from PDB, or we will use our link here. And then here is a grep command that we will remove. Actually, what will we remove? We remove HOH. It will grep HOH, and then it will remove it. And then it will save it as 1AKI underscore clean.pdb. And here I am. Here I will copy and paste this thing. But here one thing you people should know, that one PDB file is in caps. Here we have written it into the small letters, so it might give us an error. So why not we just write it down into our caps, and then it will save it into 1AKI underscore clean.pdb. I will press enter. Let me check. So here you can see that we got two files, and we can see these actually files, either water has been removed or not. So first I will remove the I will check the original file. Here is the original files, consist of 7 files. And if we check the other files, and you can see that water molecules might have been removed from that particular PDB file. You can also check it in other like in the Visual Code Studio by easily by checking it, but as I'm sure that it has been removed, so we will just follow the commands which are here. So here we have just remove the water molecules. Sometimes we need water molecules actually. It depends that what we are gonna do, but for this tutorial we will remove this water molecules. Our next thing is to make the topology file, and for that purpose we use a command which is called pdb to gmx file. And for the purpose is that we need to make the topology of the file, the position of restraint file, and a post-process structure file. So that is basically the requirement, that we just convert our file, which is the PDB, into a file which is called the GRO file. So this is command gmx pdb to gmx -f, and this is our file which we got after running the command. And then we are adding the waters, and we are using this particular model. We have opportunity to use different, but let me just copy and paste. So for the initial thing, it's quite okay that you just follow this particular tutorial. So this is our command. We just need to check that either we have this file which is in caps 1AKI. So we have this file, and then I will press enter. And here you can see that asking me I need to select the force field. I need to select 394, 96. What kind of force field I want to select. So I will stick to my tutorial that what particular field I should select. First of all, the selection of field, it depends that what kind of PDB file you contain. Here, charm36 force field is being used, which is present at the number 9. Here you can see the charm37 in our run. We can also use, in fact, the number 1 or 94 very easily, but I will prefer the charm field actually, which we want to run. Charm field is not present here actually. So either we have an option that we can download it and we can save it into library file, or we can use any of these files. So I will use this 8 number, which is the charm27, and I will press an 8 number here. I will press enter. So it has selected the force field, which is at the number 8. So our results might be a bit different from the protein, the results from this tutorial, but essentially they should be the same one. So what it did, here you can see the force field is being applied. So it's just having the chain A, and these are the residues number, these are the atom numbers. It's opening the force field, and then this is the top atoms 9 line it's showing here, and now these are the number of atoms which are present here. And then if we check into ls, here you can see I got something which is called GRO file. So we have generated the GRO file, we have generated ITP file, we have generated a topology file. If we look at the topol file actually, and it look like this. So this file is generated, and it is generated by this particular things, and it is present in this file, and this was the command by which it has been generated. If you want to look at the complete file, then you can look at that by opening it into the code, but I'm not gonna do that for now actually. And then here you can see that we have prepared this file, and this is second file, this is third file. So we got 3 files actually. And now we will move towards the next step actually. In the next step, what we got the topology files and everything which is present here. And so if you need to understand the topology and what kind of parameters are set by the charm field, you can have a look at that. Okay, if you essentially wanna install or use this particular 36 charm 36 file, you can download it. You can download it and then you can save it in this particular location. But for now, we don't need it. If you are gonna use the real-time thing, then you can download this topology file. Otherwise, we are okay with that. Okay, and then we got these things. If you look at the file, then we got these particular columns here. One is called the NR column, number of residues, then there are type, then there's a res number, then there's a what is the residue, then there's a atom, then there is a charge group, and then there is a charge, then there is a mass, and then there are certain types of the masses which are present here. So it depends that how you read this particular file to the topological file. And if you want to understand more about the bonds, pair atoms, then you can check the manuals and other things. But for now, we are okay because we just need to follow this thing that what things are present here or not. So we have created our topology file, and from this tutorial, we can analyze it. To analyze it, I will prefer that why not you people use this command code, and then you just go to topol.top, and then in VS Code, you will be able to look at this particular thing. And here you can see if I am able to minimize it actually to our window, then I will show you that how it look like. This is the topol file, and here you can see that in topol file we got these types and number residues and the charges, and all of these residues, these charges, these are present here. So this is our basically the topol file, which contains all the charges and other things which are required for the empty simulations. And at the end, if you look at this file, I want to show you, it says that it includes the water topology from this thing. And then these are the further functions and the CX, these are the restraints for each water oxygen atoms which are present here. Here we are going to define the unit cell and adding the solvents and define the box dimension and fill the box with water. So this is essentially the command which we are going to apply. So we have this file, and then I will just apply, oh, this is the other window. Here it is. So I will just apply this command, and here you can see that what is did. So it has just applied the box dimension. These are the box dimensions which are present here. So it automatically detects and checks the box. And as we had made it be cubical, we can also change it depending on our type of the proteins and other things. Okay, and now when we have defined the box, then we can just solvate it. We can add the water molecule. So our this file, which we have made from the new box, that will be converted into this file, which contains the solvation actually. And let me just apply this particular command here. And here you can see if everything is okay, then our files should be generated. So you people should be aware of that. Here you can see that first of all, we got this file, then this is a clean file, the topology files which are generated, and then there is a solve file, and it has also updated this topology file. If you remember that in topology file, we didn't have the water things, but if we open it now and then if we can see it, the things are generated. That lysozyme is now in water, and these are the solvent molecules which are present here, 1 to 5 9 form, that we got these water molecules which are present here. So along with the things, we can check these, that either these solvations are present or not. And then our next step is to addition of the ions, the waters, the NaCls here. We can also do that. For that purpose, one thing is to get a file which is called a file which we are gonna use here, that is called MDP file. MDP file, we can easily download it from here. We can also make it. But one example is present here. So I will prefer that you will just go here. I will save it the link as, and then I will save it at the particular folder where I have saved everything. I think that was in GROMACS and that was in test. So ions.mdp file. So we will save it. I have saved it. So my files is here. It's just asking some error, so I will keep it because this is Windows security issue. So then I can assemble this particular file by using this command. So I will just copying it, and then I am pasting this particular command. So here what we are gonna do, we are gonna add this ions actually. So our MDP ions file, that is not present in any folder, it is present here in our exact this folder. So I will remove that thing to avoid errors. So when I will run it, so it will say that it has generated something. It has generated already there are these water molecules. So these are the things. So it is generating the things. Let's see that it has generated something or not. So here you can see that we got this something. This is called the md out.mdp, and this is the ein file. So we got this particular file which is called this eins file, and we got an output file. Now we have atomic level description of our system, so we can pass it to that particular things, that the names are the Na and Cl, and then I will just put this command in, and here you can see it asking me few things, that what you wanna do, what are the groups which are present here. solve water molecules. What are these things? So we will choose SOL actually for the purpose, which is present at number 13. So I will press as 1, 3 and I will press enter. Here you can see that solvent atoms, few of them, 1, 3, they are replaced by the Cl, and few of them they are replaced here. So these are the systems which is showing me, and these are the things. So 0 Na and Cl it has just replaced. So what kind of molecule it has replaced with Cl? So it's written here. So we can open the file, topology file, and we can check that in the code that how many Cls are added. So here you can see that we are okay with everything. Last time we got here 12596, I think, and now we got 6 calcium here. Even we can check our topology file. I will go to code, and then I will say let's do ls.ltr. Here you can see that this file has been updated, and I will check it to topol.top file. So it will open it into the code, and I will go straight in the end. And in the end here, you can see it has added 8 Cl hairs, and these are the solvents remaining. So I will just turn it off. So we are able to add the solvation thing. So this is our box, and these are the solvent molecules which we have done. Now there is a step of energy minimization actually, that how we can minimize the energy actually. So we use the input parameter file now, which is called the minim.mdp. So again, we will just get this file. So this is a file which contains different things. So I will just right click on that. I will provide you these files if you are unable to download, and this tutorial in PDF, then you can use it actually. Okay, let me download it. So better is that you will right click, save the link as, and save it into the same name into your folder, and you will ask it to keep. Okay, and then I will just copy and paste this command. So what it needs, this is the file, and this is the solvent grow file, this is topology file, and we are gonna do energy minimization. So this was my file, but here again we need to change few things, like this is not in my folder, this is my main folder. And then I need to check that either I have this file or not. So here you can see I have this file by the same name, and then I will press enter. And here you can see that it has done something. It has just started doing the energy minimizations by using this particular file, which is the minim file. So here we have used this file, that is the energy minimization, which it has done. And now we are okay that we run our first MD simulations, first MD run on that particular minim file. If you go to that minim file, it's showing many things actually here, that it's showing that stop minimization when the minimum force is less than 1000, and these are the number of steps. So it depends that speed of your computer. Here you can change the number of steps, and then your time will be changed. If you think that your computer, your laptop is taking a lot of time, then instead of 50,000, make it 5,000 actually. So it depends on you that how you wanna run it. Okay, let me go back, and this is a command which invokes actually the MD simulations, and then I will copy, I will paste it. Here you can see that it has started the steps. So these are the steps, and these are all being run depending on the speed of your system. So these are the 50,000 steps. It has started. So it might take some time actually. Here you can see it has just started now, few steps, and but energy is already minimized because fmx less than 1000 in 298 steps. So we got our system ready in these steps actually. In some cases we need to run more steps, so it depends on how the beautiful your protein is actually, and then you can use it. So we got here energy minimization by using the MD simulations, and MD simulation, it will create some output file. So let's check that what output files these are created. Here you can see we got these energy minimization files 1, 2, 3, 4, and 5. Log is here. So if we want to check that how the log file look like, we can check the log file. And in this log file, I can open it into the code thing. And here you can see everything that how it has minimized the energy. And at the end, it will just tell you that how long it has taken on that particular date and time. Okay. And so if you wanna generate the graph actually, and you have this thing ready, so we can see it by using this command. Even we can analyze it along with, and I don't know we have we have VGX installed here or not. So here I have just give it a command and asking me that how you need it. So everything is given here, that what you need to select element 0, type element 0 to select potential element, and it's 0. So it's just to make the graphs, that how you wanna make the graphs. Element is potential energy, and then 0 is basically that terminates the things. So when I will press enter, but we need this particular program which is called xmgrace actually. If xmgrace is available, then everything is fine. Otherwise, we need to install it, and then we will be able to look at the graph like this. So when I will enter it, so it will give me that this is the potential energy, this is the RMST, and these are the total values which are present here. And if I look at ls.ldr, here you can see that it has made this particular file, which is xvg file. Xvg file, you can see it by this. You can also install this xmgrace actually if you want to. That's very easy to install that. You can install it by using the sudo apt install xmgrace, and that will be installed. But we are not concerned with that actually. We can have a look at that later on. And so we have done energy minimization. Next step is equilibration. So how we can equilibrate our system. So we have this particular command, but that purpose we need a file which is called nvt.mdp file, which is parameter file, and we can get it from here actually. I will again save it. I will again save it nvt here, and then I can also check what is in nvt file actually by using the same this particular thing. So this is let me check the name of the file actually. That should be present in this folder ls.ldr. So, oh, this is not still downloaded, so it's taking time. Maybe it's some kind of internet issue or whatever it is. It's taking a bit time. So it might be the internet, because it just take few seconds. Let me check that either. Oh, it's still not downloaded. So sometimes it takes some time due to the internet, that whether this is completed or not. Okay, let me download it again if there is an issue. So I will say it nvt. Oh, I need to keep it actually. This was the issue, because Windows has got some errors in being that these are the suspicious file. Here you can see that we got an nvt file, so we can check what is present actually in nvt files, and we can open it into the code. And here you can see that these are the systems, and these are the number of steps, which are the 50,000, and the time is 2 femtosecond after it will record every point actually. And these are the bonding parameters. So you don't need to be worried about all these things for now. And usually you don't need to worry about in other proteins actually. But in few cases you need certain changes. So I'm okay with that. And then I have got this particular command. I will copy it and I will paste it. But as this file is not present in my inputs, that is present here. So I will run it like this. So it has created the file, and then now it's ready to run by md simulations, mdrun. So I will say it mdrun it. So it's again 50,000 steps, means the 100 picoseconds. Actually, we can lower down the steps if you want to. So we can just change the steps from 50,000 to 10,000. So it will run very quickly, actually. But it depends that what is the speed of your computer and how long it usually takes. So let's see that how long it takes for the regularization, and then for the next time in your own laptops, if it takes a lot of time like half an hour or hour, then you can change the number of steps, and then also you can change these picosecond actually. So it depends that how fast is your laptop and how good it's going on. So let's wait that how it will work, and then we'll back here. Or we can do one thing, that I'm gonna just stop it here, and why not I just give this thing just only the 10,000 steps instead of the 50,000. So it will run very quickly. So I will go here, and then I can change it to this particular thing. So this is actually the 20 picoseconds, which is actually equal to 20 picoseconds now. Okay, I will save it, and then I will rerun it. So it's just only the 20 picoseconds now. Oh, maybe it's not saved actually. Okay, maybe it was in its, oh, we need to make a file actually first. Every time you change that particular thing, we need to run this command beforehand, which is the gmx for making this particular files. So when I will run it, so it will make the file, and then further we need to run this particular thing. And here you can see it's just only the 10,000 steps and 20 picoseconds. And in 20 picoseconds, then it will finish automatically. And after finishing it, then we can also create a graph like this. So that is the GMX energy. So that is the temperature graph, which we are able to create. So I can just copy, and I can paste it after. So even for the 20 picosecond, it's taking a lot of time. But along with that, in the folder, if we check, it will be creating some file, or there is a one way to check it, that how well it's doing. So we can check the files. That here you can see that if we go to the GROMACS, and then we are in the cd test file ls.ltr, and here you can see that we are getting nvt.log file here. Okay, and we can check this actually log file into our code, that how long uh, it has been run. So I can open it into my code file, and here you can see that it's just letting me know that how far it's going on. So it's still working here. So it's just trying to do that. Till now, 2,500 steps has been completed, and this is a 5 picosecond time, and it's still working on. So you can check it here, or you can check it like this. You can tail it. You can tail, and then you can ask it that log file, and here you can see this is a tail, and it's showing you last few lines of that particular log file in the real time, that how the energies these are being created or not. Here you can see the file is running, but it's not verbose. It is not telling you the detail. You can get the details either by opening it, the file into the code, or you just tailing the file by using tail f, and then this is the detailing or tailing the things. And ultimately you are tracking your time, that how long it's taking to run GROMACS temperature equilibriation. So let's wait. So this is the next step. Now 5,000 steps has been completed. Time is completed for 10 picosecond. So let's wait until 20 picoseconds are completed. Then after completing 20 picoseconds, then we can run this particular file. We have to type 16 that we want a graph against the temperature, and then we can see the equilibration, that how temperature is being equilibrated. And after the temperature thing, we have to do the other equilibration things, like the pressure ones. And then we will go to the next step actually. And let me check again that. So it's just going towards the 15 picosecond. So for ideally, we have to run it for the 100 picosecond actually. When you are doing your actual things, you can do it 100 picosecond, 200 picosecond, 500 picosecond, depending on your computer. So 15 picoseconds are done, 7,500 steps are done. So it will finish at 20 picoseconds actually. So after 20 picosecond, it will say that it is finished. And we are just checking the files here. So this is how the files are created. I will send you these all files which are in a zip folder, which are being generated or which will be generated as a result file. And I will also let you know, I will make a video that to show you that how we can install the xmgrace and see the graphs which we have created earlier, and we will create here. So it's almost gonna end. The first one we will make, but afterwards it will be very easy for us to check that either everything is done or not. Here you can see that it has been finished. It has taken means 6 nanosecond per day can be done, and 1 nanosecond will take 4 hours on my this laptop on this system. Here you can see that it has been done. It's just showing you the course seconds time what it has taken. And if you wanna make a graph like this, you can go to you can use this particular graph. I will use 16. I will use 16.0, and it will create something. This is the average temperature. This is the RMST. I will go to the second equilibrium stage actually, in which we are gonna use this npt file, which is for the pressure. Then again, I will go here, I will save this file, and I will save it as such. So if you ask me to keep, I will keep it. And again, here I will do the ls.edr. Here you can see this npt file is here. I will open it, npt, and here again I will change the steps actually. And here it says 250,000 steps. Actually it's gonna run, it is about the 500, but again I will not do that. I will just do that for the 10 for your tutorial thing. It is far more less, but it's totally fine. So I will just save it, and I will ask it to make the files for me which are okay for that, and it has made the files. So okay, it has not made the file because we didn't check out this input actually. So let me change this particular thing, and then let me run it. So it has run, it has completed the things. So let's check the files, either they are generated or not. So LTR, here you can see the files are generated. So we are okay to go in the next file. So that is the mdrun, and then here we have run our mds actually. So 10,000 steps. Again, if we wanna check our log file, we can check our log file here, but this time this is an pt.log file which we are gonna check. So it's just telling it 5,000 step 1 picosecond are completed. So it will take long time actually. It will take a lot of time here. So I'm just gonna pause it for a while, and so it will just finish the things. Here you can see 2 picoseconds are completed and 1000 steps are completed.